No, IT has not replaced the bulb. It's ridiculous. It's not the bulb, though. They have to replace the whole projector. Still, should have been done by now. What week are we in? Yeah, exactly. I put up all the stuff. Class average was 71 or something like that. There were lots. I was happy with it. All right. Well, today I've got to deal with a different headphones or microphone, I should say, because my wireless one, the battery's not charged. So I think the audio might come out a little bit different on this video. So ahead of time, I apologize. If you do watch it, it may sound weird. Okay, let me start class with any questions over anything. Homework. Ah! Number 7. Find the slope of the tangent line to that curve at x equals a. Were you having problems with that x cubed? No? All right. So it says find the slope of the tangent to the curve y equals 3 plus 4x squared minus 2x cubed at the point, or at x equals a. Is that the part of the problem you want me to talk about? The actual finding, yes, the tangent? Okay. So which formula did you use? F of x minus f of a? Okay, so the slope of the tangent line, or I'm sorry, the derivative, I'm going to start using that language. The one that you used was the limit x approaches a, f of x minus f of a over x minus a. If you have not, please turn in your quiz. I won't accept it later. Make sure you turn in your quiz if you're just coming in. Make sure you all turn in your quizzes. So this will be limit x approaches a of, let's see, you just wrote f of x out, right? And then you wrote f of a, which is this with a's instead, but the minus, right? So when you do the minus, it'll make it negative 3 minus 4a squared plus 2a cubed. Then all of that over x minus a. Okay? And you do get some canceling here. You got 3's go away here. And that's it. Right? That's it. I can already see where you may have had some issues. But let's think about this. The idea is to get x minus a to cancel, right? So you really would like to have up here somewhere an x minus a that factors out. So let me rewrite it and just tell me if you believe that I could rewrite it like this. 4x squared minus 4a squared. And then minus 2x cubed plus 2a cubed. All over x minus a. Now that's just my first instinct on this. See if this is going to work or not. Now, why do you think I wanted to go that way with it? If you factor a 4 out of this, what would be, just here, don't worry about these. If you factor just a 4 out of this, what's left? X squared minus a squared, which is the difference of squares. And it factors to be x plus a, x minus a, which is what I want down here, right? So I'm kind of like foreseeing that right now. I still don't know if this is going to work. So let me rewrite. Limit x goes to a, 4 x plus a, x minus a. But that's just this top left, right? That's just this. What do I still have up there next to this? This right here. So how about this? How about I factor out a 2? How about a negative 2? Why in the world would I factor a negative 2 out? What would be left here? X cubed minus a cubed. Do you recognize x cubed minus a cubed as something? Difference of cubes, and there's a formula for that one. And it happens to be x minus a, in parentheses, x squared plus xa plus a squared. But you'd have to know the difference of cubes formula for that to work out. Shall I continue? Yes. Okay, so we have limit. I think I would have probably gone to the other formula right about when I saw, I don't know, this right here. I would have maybe tried the other one. Remember what I said the last time. Don't get fixated on one method only, because you want to be equally comfortable with both. All right, so this difference of cubes became this thing right here. And then the negative 2 is out front, and then this was this. Notice that you have x minus a, right, in each factor. In the top right here, in this factor, you can pull an x minus a out of this one, and then cancel it with the bottom. So can I just cancel them now? All right. So what I'd be left with is limit x approaches a of, what is up there, 4x plus a minus 2 times x squared plus this, my gosh, okay, over, oh no, no more over, right? No more over. So what do you do at this point? Let all your x's become a's. So this becomes, bless you, bless you. Okay, that's enough. Right? That's what would happen if all my x's become a's. So I get 2a here times 4, that's 8a. And then over here, this is a squared plus a squared again, plus a squared again. That's 3a squareds. Then times negative 2. So minus 6a squared. That it? That's it. Did I address your question? Did I address your question? Are we good? Anybody do it the other way? Did you get the same thing? Yeah. Was it any cleaner? A little, or same? Still kind of tough. Yeah. From this is a squared right here. So a squared plus a squared plus a squared is 3 of them. Then times negative 2, that gives you negative 6. Now, do you remember I said we're going to, right here? A plus a is 2a. Then, yeah, it's addition. No, it's okay. We good? All right. I don't want to get too far ahead here, but I want you just watch what I do real quick, okay? What would happen if I take this term right here? Forget the 3 for a second. Take this term right here, and I take that 2 up here, and I bring it out front and multiply times 4. What's 2 times 4? 8. And then I want you to subtract the power. 1, just reduce that power by 1. And what would you be left with? You would have 8x, right? Okay, what if you brought this 3 down, did the same thing? 3 comes out here, hits this, it becomes -6 or -6, and then x what? Squared. Okay, doesn't that look kind of like this, except the a is at an x? 8, right? You see that? And then you see this 3, since it doesn't have an x, it just goes away. Okay, these are the shortcuts we're going to learn. Yeah. I don't think we're going to get to it today. Okay, that's what's known as the power rule. And so if you were to ask a Cal 2 student what the derivative of this is, they would look at it, and in 3 seconds they would be able to tell you this. Oh, they just said, yeah. So we're not there yet. We're there next week, all right? Now, but you got to be careful what you wish for, because along with the rules becomes more complexity. Because right now we're very limited on what we can do as far as this work is done. Because as we can see, the algebra gets harder and harder. If this were the 5th power, and that were the 4th power, something like that, imagine the work in here. It would be a disaster. Then throw some natural logs in there, or sine functions, and right? So what happens is we find a way of coming up with rules and properties so that we can handle the bigger, more complicated, real-world things. Make sense? All right. But for now, like I said, we're torturing ourselves with the limit, or with the limit definition. What's that? The b on 7? Tangent at 1,5. Well, that's 2 separate problems. They want you to find the equation of tangent line at a certain point, then another one. So, okay, so I'll just do one of them. At the point 1,5, remember the equation of our tangent line is always this. Right, that's the equation of the line. The tangent line, this number right here, comes from our derivative. Right, this is our f prime right there. But we want it at what value? If I'm at this point, what value am I looking at? Like 1. I'm going to be replacing the 1 for the a in that thing we just had. So what I'm really going to find over here is what's f prime of 1, which we said was 8 times 1 minus 6 times 1 squared. So that's what, 8 minus 6, so 2. So the slope of this line is 2, and then everything else just fill in. That's right. Did that answer your question? Okay. Remember, the power of doing the derivative in general was that we get an answer that we can continually use over and over instead of having to go through the limit, each time if we want to look at it at different places on the graph. All right, today we're going to explore this whole idea of trying to get this derivative and just talk about the power of having such a general answer. All right, and what it really tells us about what's going on with our function. So for 2.2 today, we're looking at the derivative as a function. Now, like in the previous example, right? Like what I was asked about just now, we said that y was equal to 3 plus 4x squared minus 2x cubed, right? That's what we were looking at, and we were asked to find, slope of tangent line, whatever. Well, if I change this to f of x, so I'm just replacing y with f of x, then I would hope that everyone here would agree that f is a function, right? F is a function. Now, when we go and we found this earlier, or a minute ago, we did the derivative, right? I wrote it like this. This meant the derivative of that f function. And we came up with an answer of 8a minus 6a squared. After all the work we did, right? Do you agree that this, again, is another function? If we don't lock down what a is, then the answer should be a function. So we start with the function, we do something to it called taking its derivative, and it spits back a function to us. That makes sense? It's kind of like this. If we look at a function that we've known, like f of x is x squared, and we take the number 2 into it, and we run 2 through it, it gets squared and comes out as 4, right? We take the number negative 1 through it, it spits it out as what? 1. Okay. A function, by itself, a function takes a number in, spits a number out, right? What we're doing now is something completely different. We're starting with a function called f. We're doing something called take its derivative, and then it's spitting out what? A new function. The derivative is actually called a functional operator. It's a function, but not really, because it eats functions and spits functions out. Does that make sense? So we call it a functional operator. All you need to know right now is that when you have a function and you take its derivative, it returns a new function. Not necessarily the same thing you started with. Okay? So if it does return a new function, then couldn't I rewrite that new function right here? I could have just replaced the a with x. I mean, isn't the a there a dummy variable? I mean, writing it this way and this way are the same exact things. If I say, hey, plug 2 into this function, you're going to get the same thing as if you plug in 2 into that function, right? So this dummy variable really doesn't matter. The reason we like this notation better is because you start out with a function of x, right? And you end up with a function of x. So we just swap in the variables so that our x's are kind of the same. Y'all okay with this? All right. So what I'd like to do now is start with a very generic example here. Let's look at f of x is x squared. And I want us to find f prime a. So this is like what you had to do on your homework, right? You go limit. You could do one of two formulas, right? H is 0, blah, 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 blah. Or you could have done the limit, what, x goes to a, blah, blah, blah. Yes, you could choose. Well, I'm not going to show the work, okay? Let's say you do that and you get your answer. By the way, let's cheat. It's the 2 comes out and then x to the first power, so it should be 2a, shouldn't it? I'm not showing the work that goes there. And now let's convert it over to the variable x, so everything's in terms of x. And I'll do it in green. All right. So if you start with f of x is x squared, and you take its derivative, you get 2x. Since these are both functions, can't I graph them together? Like, can I draw both of those? And that's what I'd like to do. I'd like to draw both of these together so we can get our heads around geometrically what's happening. Like, what's the connection between the two? Here we go. Get out the graph paper. No, you don't need graph paper, all right? This would make my job a little easier. F was red and green, so x squared starts out at the origin, right? 0, 0. You go out to the right 1, you go up 1. You go out to the right 2, you go up 4, right? And then you draw this parabola that goes like that. That okay? Same thing the other way. That's f of x is x squared. Now, what does its derivative look like? Which I said was green, right? The derivative we said was 2x. So if I graph that, that's a line, right? It also goes through the origin. Has a slope of 2, so up 2 over 1, up 2 over 1. Man, can't draw a straight line. There we go. So that one is f prime of x is 2x. Okay, everyone see these two pictures? What does the derivative of a function represent? It all started from the idea of slope of tangent line, right? That's where it all started. So this green function somehow represents the slope of the tangent line of the red function. So what I'd like for us to do now is pick some arbitrary point. So I'll let someone volunteer an arbitrary value of x. Now make it a decent, nice value. 2. Okay. So if I go out to 2 on the x-axis, 1, 2, and I go to the red function, right? What is the value of the function there? 4. So if I plug it, that point right there is the point 2, 4. Right? Now, what is the value of the derivative there? So I'll connect that. That's from here, right? If I come over here, the value of the derivative is 4 also, right? What does this 4 mean compared to this 4? I want you to compare these, the yellow one and the pink one. Who can explain, who can let everyone in the class kind of know what the difference between that 4 and that 4 are? This is the point that comes off the original function, right? So the 4 here is the height of that function, isn't it? Yes? It's how high the parabola is off the ground. The 4 here represents the height of the green function, yes? But how is that related to this one, to the red one? That 4 should be the slope of the tangent line. So if I were to imagine that the green one's not here, oops. Okay, imagine the green function's not there, and I were to ask you to find the slope of the line right here, the tangent line. Do you all agree the tangent line would look something like this? That's a terrible line. But do you agree that the tangent line at this point would look something like this yellow line? And guess what the slope of this yellow line is? It's 4. This value right here is the value of the derivative at 2, which is 4, which represents the slope of the tangent line of the red curve at 2. Let me try. You pick 2, which is kind of a somewhat confusing. I'll do another one, yeah. Uh-oh. Trying to bring back my picture here. Okay, so let's do -1 instead. I'm going to pick we're going to pick -1. What's f of -1? So I come over here, I plug in -1. It spits out this point, so that's where I am. So 1. So if you look at that as a point, negative 1, 1, this is the x value that went in. This is the height of the function, right? Now, if I go and draw a tangent line right now, it looks like the tangent line is going to be something like this, right? If I did, it would be that blue line. What's its slope? What's its slope? Negative 2. Why? Because if you go to the derivative, go to the green one, what's its value at negative 1? It's negative 2. So the point down here, f prime of negative 1 equals negative 2, is the negative 1, negative 2, that point. This right here is the slope of that blue line. Do y'all see the connection? So act like we don't know what the red one is. If I say negative 2, right? What's the slope of my parabola at negative 2? Is it positive or negative? What's the slope of the tangent line? It should be negative. Why? Because the derivative is down here, negative, right? Where is the slope of this parabola? Where are the slopes of the tangent lines on this parabola positive? To the right side of 0, because that's where the green one is above. So what we're going to try doing right now, I don't know if I've shown you enough, is I'm going to give you a graph and I'm going to ask you to draw its derivative to kind of guesstimate what it looks like. And then I'm going to give you a derivative and ask you to draw its graph and work backwards and see how we do with it. We'll start with is a pretty basic one. The red graph is f. That's f. I would like for us to sketch f prime. Sketch its derivative. Yes. The derivative, if you've watched a little bit further, then at a corner or cusp, the derivative doesn't exist. But we're going to see that when we draw its derivative. We're actually going to see it. You'll see why it doesn't exist. So let's try and find the derivative of this function as a graph. What can you tell me about this? See this part of the line right here? Can you tell by my drawing what the slope of that? Like if I pick a point here and ask you what's the slope of the tangent line, it would just be the slope of that line, wouldn't it be? Pick any point on this line, the slope of the tangent is just the slope of the line. You can tell the slope is 1 because its rise is 1, run is 1. 1, 1, 1, 1, right? So the slope of the tangent line anywhere to the right of this point, which is 1, anywhere to the right of 1, to the right of 1, the slope is 1. So my derivative needs to stay as a constant 1 value out the right side like this. What about to the left of 1? If you're over here somewhere, what's the slope of this line? Negative 2, right? Which means the derivative must always be negative 2 to the left of 1. So if I go down, negative 2 is this, right? It's supposed to be straight. Do you all see that connection? Yes. Because if I were to tell you to pick a point on here, right? Pick a point anywhere on this section and ask you what's the slope of the tangent line right there. Since it's a line, it would be the same as the slope of the line. Rise over run here is actually down 2 over 1. So down 2 over 1 is negative 2. The big question is what's happening at 1? Don't we have a jump in this blue graph? So what we're going to do is we're going to put a circle here and a circle here. So the blue graph jumps. So you have a break in the graph, which means it's not the derivative doesn't exist. But that's beyond what we're going to talk about right now. All right, let me try something else, okay? Try something else. If this blue function is f, I would like for you to find its derivative, or sketch its derivative. So when we're talking about sketching the derivative, we want to draw what's happening to the slope of the tangent line, right? So what's happening right here? What's the slope of the tangent line? 1, anywhere in here, right? So I come down to the x-axis. My derivative needs to be between here and here. It needs to be up 1 and stay 1, right? So I draw like this. Now, between here and here, what's my slope? -1. So my derivative needs to drop down and stay -1 between there and there. What do you think's happening between here and here? We have this jump, right? So we have, just put little circles like that to represent a jump in the graph. Then what happens when I get to this? Slope is 1 and then -1 and then 1 and then -1 and then 1. Right? So it's just alternating back and forth. Yes. Well, it doesn't matter. I mean, the idea of the open circle is that it doesn't exist there. Can you all kind of see the connection here between a derivative and its graph? I mean, sorry, a function and its derivative graph together? You try something else. Okay, here's the function. That's it. Draw its derivative. Now this looks like a rational function, right? Which has an asymptote. Looks like the y-axis is an asymptote. So I'm acting like the function does not exist to the left, all right? So let's not even worry about it. Can anybody give me just a general, very vague description of what the derivative is of this function all the time? Like, is it positive or negative? Negative? Pick a point, any point you want on that graph. Draw me a tangent line. What's the slope of that line, positive or negative? Pick another point. Negative. Pick another point. Negative, right? Pick another point. It's hard to see it, but it still has just a slight pitch to it, doesn't it? Still just a little bit negative, right? So do we all agree that the drawing that we have of the derivative should always be negative? So it should always be below the x-axis. However, it's not constant. So it's not like over here where we said, okay, between here and here, the slope is always 1, then -1, then 1, then -1, then 1. It's actually, the slope is changing, isn't it? So I'll help out by picking this point right about here. Right about there, what does it look like the slope of the tangent line is? About. Doesn't that look almost like a perfect diagonal? I mean, almost, right? Where it would have a slope of 1. Sorry, not 1. -1. Do y'all buy that? So if I imagine that right here at this x value, my derivative has to be -1, I put a dot there for -1. Does that make sense? The slope of that black line is represented by how high up and down that red dot is. What would happen if I pick a point that was further to the left, like this one? My slope is going to become steeper. It's still negative though, right? But it's a bigger negative number, isn't it? A bigger negative number, which would mean that I would need to come down here and go, okay, right here, I need to go to a bigger negative number. Now, how far do we go? It's hard to tell. So I'll just go, let's say, to here. And what would happen if I went even closer over here? It would get even steeper, wouldn't it? But still negative, which means that this right here would drop down even further. Do y'all see what's happening? I can't draw it on here, but now pick a point over here. Let's try something on this side. Is my slope still negative? Yes, but it's actually a smaller negative number, isn't it? It's not as steep as this one. That one was -1. This one is not quite that steep. So maybe it's like -1/2. So that means below that, I can put a dot somewhere like this. And as I keep moving to the right, what does my slope approach? What is it getting closer to? 0, which means my red function must approach 0. So you wind up getting almost like a reflection of itself, right? When you connect these together, that red graph is always below the x-axis, which means it's negative. That corresponds to the fact that that blue graph always has negative tangent lines. Question? Questions? Yes, just a little, just marking of it. Of course, it extends forever, but it's just to give us an idea of what's happening there. Like if I were to pick this point right here, you see that one right there? The tangent line is obviously not that one, right? I mean, you're comfortable with what we mean by tangent line? It's just, instead of drawing the whole thing, I just draw a little segment of it. And as I move along the curve, that little line changes. All right. How about this? This will probably be one of my last examples of this. That's F. Whenever I'm trying to draw a graph of a derivative, I always like to start with something I know. Like I would say between here and about somewhere in here, if I take any point in here and ask for the slope of the tangent line, you would say the slope is what? 0, right? Slope of a flat line is 0, which means that the derivative, which I'm going to show down here in red, between here and here would have to be 0, wouldn't it? Which means I just draw it on top of the y-axis like that. We okay with that? Then, as I continue along here, what happens to my derivative? It's 0, but then all of a sudden it starts becoming, my tangent lines start becoming negative, right? Slopes of these start becoming negative. And as I move down, they appear to be getting what? Steeper and steeper? Steeper and steeper negative, which means bigger and bigger negative values, doesn't it? For the derivative. So my graph starts becoming negative, but the values start getting bigger and bigger and bigger. And eventually, it looks like my drawing's not that good. I really can't tell what's happening. But do you agree with the format of the graph? Yes? Now that took care of this side. Let me go on this side. Do you agree that over here, between here and here, my derivative is going to be 0 in here? Yes? So that means I go to my x-axis, draw 0. Now what's the difference though on this side? Yeah, if I start picking values over here, positive slope, they look like they're getting steeper, which means bigger and bigger positive values. So it starts, positive means above the x-axis, but they start getting bigger and bigger and bigger. And so it looks something like that. Any questions? So in your homework, you're going to have a set of problems where they're going to give you a picture of a bunch of graphs, like a bunch of functions, and a bunch of derivatives, and you have to match. Like match the graph to its derivative. Match the graph to its derivative. And then there's another one where it gives you a function, it says draw the derivative, which is what we were just doing there. And these don't have to be perfect, exact answers. You just have to be able to get the general picture of what's happening, all right? Yes? Now, why in the world is this important to us? Why do we care, right? Who gives a damn? Well, here's why. Here's kind of where we're headed, just to give you a little background. Let's say I have a function. Do you remember the farmer problem? Farmer wants to build a fence, has 800 feet of material. You give me a formula that represents the maximum, or the volume as a function of one side of the fence. Remember that, right? Well, what it turned out to be was a polynomial, some function. And we want to know what would give us the most area or something like that. So if I want the most of a graph, check out a graph. This is a polynomial function. What if I wanted to know the highest point on this graph? Tell me about the tangent line there. What's the slope of the tangent line at the highest point on a graph? 0. What's the slope of the tangent line at one of the low points of a graph? So if I want to know the highest and lowest points on that graph, right, I need to go look at its derivative. Yes? Because if I graphed its derivative, right, let me graph its derivative. Tell me what's happening to its derivative at these 3 points. Where would the picture of its derivative be here? 0, so you're telling me on the x-axis? And then you're telling me that the rest of the function would be doing something, right? Whatever. Doing like this. I'm just kind of sketching this. That's what the derivative might look like for this, right? So you mean to tell me that if I want to know where the highest and lowest points of this graph are, that I actually need to find the x-intercepts of that graph? Yes? And that's what we'll do. Does that make sense? If I want to know the highest and lowest points of a graph, if I can find its derivative, I just need to find the x-intercepts of the derivative. And then I will know, well, potentially the highest and lowest points on the graph. Now, in college algebra, we were told that when you were given a parabola, this point up top was called the vertex. And they gave you a formula for that, didn't they? I will show you that formula comes from calculus. All we did here is we said, okay, look, what's the slope of the tangent lines over here? Positive, right? And then what's the slope of the tangent line at the top? 0. So if I graph its derivative, it's 0 here. It's positive over here, right? On the other side, what's the derivative? Negative, so it's down here. So guess what? To find that highest point, all I have to do is find the x-intercept of a line. Right? So we'll do it. I'll show you exactly how this works. But this is the big picture of where we're headed. Anytime we have a graph, anytime we have a function, and we want to find its highest and lowest points, we're going to resort to the derivative to do it. Okay? It's going to help us do it. Who's taking more math? Who's got to do Cal 3? Okay? I don't want to freak people out in here that aren't going to take Cal 3, but where is it? There it is. Maximum, minimum values. Like what I'm talking about right now, that graph that I just drew, and then we drew its derivative and said it's the x-intercepts. Finding the highest and lowest points on a graph is a fundamental goal of a lot of math that we do. If I'm running a business and I want to know, okay, how many, I've got some model that says, here's my profit, and it goes up and down. It's always a function of maybe the number of employees I have, or I don't know, there's something. Your profit's connected to something. You want to try and find that optimum place, right? I'll give you a better example. If I'm making iPhones, right? Then there's a certain cost to make the iPhone. And I make money off of each one I sell. Now, should I go make 40 billion iPhones? Should I say, we're going to set out to, our goal is 40 billion? No, there's not even that many people on the planet, right? So that to make 40 billion would make our cost way above what we would bring in, right? So the goal for a company like Apple is to try and figure out the less that they produce, the less it costs them, right? But they have to have enough to satisfy the demand. So there's an actual curve that shows if they change the number of units they make, how much it costs them to make that many, and how much they bring in for that many. And their goal is to try and get that to be the highest, right? They want to make money, right? To do that, they have to find the top of that function. I hope this is making sense. And in Calculus 3, it's the same exact principle. You have a function, but this time it's a surface. So now you're in three-dimensional space instead of two-dimensional space. And you're just trying to find the highest and lowest places. Things like this are functions where you have more than one thing coming in. So like, how many of you taken chemistry? Have y'all seen this formula? PV equals nRT. This is a formula that relates the pressure, volume, and temperature in a gas, right? Or something, right? Ideal gas law. Okay, so good. Well, the main three things in here are pressure, volume, and temperature. And so if I tell you what pressure and volume are, can you tell me what temperature is? Yes? Or if I give you volume and temperature, you should be able to tell me pressure. Well, I need to give you two things for you to give me the output, right? That's what this in Cal 3, what you're doing is you actually have two inputs and one output. And you're trying to figure out, what do I need those inputs to be? Inputs, what values do those inputs take on to get the highest and lowest thing out? So like, what's the highest pressure I could get, or something like that. And then you just find the top and bottom of this. But that's what we're doing, but we're in two-dimensional space, all right? You go to Cal 2, you do other stuff. In Cal 3, you blow it out to three-dimensional space, and then you go out to n-dimensional space, which you start to lose the visualization of it. But we got to start somewhere, right? That's where we are. But you see the idea, though, right? I mean, I'm answering for you. You see it, right? Yes, you do. I mean, do you see this? This is going to be fundamental for you, is whether or not you see the connection. Right? Okay, so we are trying to figure out a way of maximizing a function or minimizing it, depending on the picture. This picture was better. To do that, we need to investigate its derivative, which is why the derivative is valuable. I hope I've made it seem somewhat reasonable. Now, there are times when a derivative fails to exist for a function. And there's a couple of scenarios. When does derivative, or I'll just put f prime, fail to exist? And I know some of you have watched ahead. Someone give me an example of when the derivative would not be defined, when it would, a cusp. So a cusp would look like this. Comes up to a point and then comes back down. And then I heard what, corner? A corner is a sharp corner like that. And then another one, it's not continuous, where you jump. Now let's talk about why your derivative would not exist. Now look, it's important that you understand. Here's A, here's A, here's A. What we're saying with these three pictures is f prime of A does not exist. Pardon me? All these pictures. What we're saying is that only at this value does the derivative not exist. What is the derivative again? Geometrically, what's the derivative? It's the slope of the tangent line, right? If I stand right here on this graph, right there, somewhere over here, can you tell me what the slope of the tangent line is? Right there, do you know the slope of the tangent line? You can figure it out, right? I mean, it looks like it's defined. What about over here? That okay? But what happens is you start getting closer and closer to this value A. It tries to become a vertical line, right? Vertical lines are not defined, right? If you look at what's the slope of a vertical line, it's undefined. Therefore, the derivative would not exist at that value of A. How about on the other side of A? Would the derivative exist? Yes, right? I can find the slope of a tangent line here somewhere. How about over here? Does the derivative exist over here? Yes. How about on this side? How about right there at A? And that's kind of a weird one, right? Because you may want to say the slope is 0. But think about it. As you come in from the left, I wish I had my wireless headset. When you come in from the left, your slope is always what? Like -1 or something like that? And then as soon as you get to A, what happens? As soon as you get past it, it's an immediate jump, right? And because of that, it's not a smooth transition. The derivative doesn't exist there. Same thing here. Your derivative here is positive, positive, positive. It's fine. And then all of a sudden, it has to flip to a negative. And because of that abrupt change, we say the derivative doesn't exist there. Okay? Point A, I could have called it C. I could have called it D. I could have called it a lot of things. Okay? So there are certain places where it doesn't exist. Also at asymptotes, You know, if you have a graph, let's say you had a vertical asymptote, this. But see, the thing here is that your function doesn't even exist there, right? At a vertical asymptote, your function's undefined. So there's no way you can talk about its derivative being defined there. If the function isn't defined there, you don't even talk about derivatives. All right. Now let's get back into some of this limit stuff, all right? And this will be the end of the limits today. And then next class, we're going to get into the rules. From now on, we will use f prime x instead of f prime a. So I'm going to replace the dummy variable a with x. Now this creates a problem because what were the two definitions we had for the derivative? Remember, it was f prime of a was limit h goes to 0, right? F of x plus h minus f of x all over h. And the other one was, wait, hold on, a plus h, sorry, f of a. That was the first definition, right? The other one was f prime of a was limit x goes to a, f of x minus f of a over x minus a. Those were the two that we've been using, right? But now I'm going to start using this notation, f prime of x, instead of this to stress the fact that we're getting a new function. Which of these are we going to have to put to the side then? The second one. Why? Because if I'm going to replace the a here with x, what's this going to say? X goes to x of f of x minus f of x over x minus x, which is basically 0 over 0, which doesn't make any sense, right? So we will have to scrap this definition and we will stick with this. Now you may be like, wait a minute, hold on, why didn't you tell me to, I should know that one instead? And that's because this is the end, okay? We're done with limits. From now on, after today, when I ask you to take a derivative, you will go to the rules. Now on your next test, if I tell you find the derivative using the definition, you must use one of those formulas. If I say find the derivative and I do not say use the definition, you can use the rules, the shortcuts. Are we clear on that? I'm going to repeat it. It's going to be recorded. Okay? On the test, when I say find the derivative using the definition, I mean you must use one of these formulas and you must suffer through the limit through the entire problem. When I say on a test, find the derivative, and I do not tell you use the definition, you may use the shortcuts. If I say use the definition and you use a shortcut, you get no credit. No credit. It's kind of like what we did earlier. 3 plus, what was it? 4x squared minus 2x cubed, right? Now, because of the little shortcut I told you, if I said find the derivative of this, you would say, oh, he said that if it's a number, it just goes away. Then he said, bring this out. That's what, 8x and then minus 6x squared. So if I said on this test, there's your function, use the definition to find the derivative, and you did this, 0. Okay? 0 points. Because the idea is to make you use the limit, to show me you're comfortable with it. Are we clear? I hope so. What's good about this, though, is that you can check your answer, right? You should be able to check your answer pretty quickly. Say, yeah, that matches what I got with my limit. All right. I'm just wondering how many more limits we want to take. You've reached the limit of the limits. Let's just practice with the notation one time, okay? One more example, something I haven't shown you. Find f prime x where f of x equals x to the 3 halves. Now, the way it's written right now, could you use the shortcuts on a test? Yes. So I need to put here, use definition. So I'm going to say use definition of the derivative to do this. Well, because I'm putting f prime of x, you're kind of forced to use that other notation. Limit h goes to 0. F of not a plus h, x plus h, minus f of x all over h. So that's the same formula you've been using with all the a's replaced with x's. This is limit h goes to 0. Now, when I plug x plus h into this function, I just get x plus h raised to the 3 halves minus just x to the 3 halves, right? All over h. And what I'm hoping to get here is an h to cancel, right? Trying to. What in the world are we going to do with this? We must be careful because there's addition right here, right? You can't just put this power on both of those. You know what I'm saying? Why not? Was that the question? Well, you're asking a profound question, so let's answer it. If I have x plus 2 squared, why can that not just be x squared plus 4? Why not? Someone told you couldn't do that, right? You can't just square those? What middle? I don't know what you're talking about. Oh, yeah, because when you FOIL out. But why is this not okay? I mean, why is it not? I understand the foiling part of it, but let's say that the distance from here to here is x. Right? Say distance from here to here is x. Okay? Let's say that I measure out with a ruler and I say that's 2 and that's 2. Understand? So I have some arbitrary distance x and then I add 2 to it. On this one I have x and I add 2. Got it? Okay. Then what is the distance from here all the way down? It's x plus 2. What's the distance from here all the way over to here? X plus 2. All right? So what is the area of that green square? What's the total area of this square? It's x plus 2 squared. Agreed? Okay, now check this out. What's this square? Okay. What's this rectangle? 2 times... Oh, wait, you know what? Let's do this one up here. What's this one right here? 2 and 2, there's your 4. If you think that this is just this, then you've only accounted for this portion of that area. You still need these other 2 places right here. And this one is 2 times x, and the other one over here is the same thing, 2 times x. And so when you put all those together, you get x squared plus 4x plus 4. That's a geometric convincing that you can't pass a power through addition like that. I just did that because maybe you've seen it, maybe you haven't. All right, so back to this. We cannot put this 3 halves through. I'm just concerned about what you're doing there. I'm just concerned about what you're doing there. You're looking at notes? Okay, all right, that's all. Just want to make sure. I'm just looking for guidance here. Someone's got to take a swing at this. Any ideas? Conjugate. What is the conjugate? You mean the conjugate right here of this? What's that? No? What? Okay, then other suggestions? Wait, say that again? Uh-huh. Yes. X times the square root of x. Okay, yes. Okay, so let's just first talk about what it means to raise something to the 3/2. That's it right there, right? To raise something to the 3/2 is the same as cubing it, but taking the square root. Or taking the square root and then cubing it. Yes? Do y'all follow that? That's kind of important because if you cube this root, it's this times itself again. And the first two, I think that's what you were getting at. The first two here together give you just what? X plus h. And then you have this one. That's what you were saying, right? I'm just trying to show why it is that way. So this is really just limit h goes to 0. I'm not knocking the conjugate idea out of the water yet, but I'm just going with this idea right now. If this piece right here can be rewritten as x plus h times square root x plus h, then how can you rewrite this one? X times square root of x all over h. Okay, I'm okay with that. Now what? You want the conjugate of this? All right, I have no problem with that. Conjugate. So it's the same exact thing. Plus though, right? I hope this works. We know the middle term should cancel, right? What happens to the outside terms? Be real careful here. This times this. That means all of this times all of this. Let's do the x plus h. X plus h times x plus h is x plus h squared. And then what's this x plus h and this x plus h under the root going to turn out to be? An x plus h. So I have an x plus h squared and an x plus h. Is that correct? Yes. I have an x plus h squared and then an x plus h, which is really just x plus h cubed. All right. Leaving some work for you there. X plus h cubed. And then what does the outer one turn out to be there? Same kind of story, right? X times x gives you this x times this x gives you x squared, and then the root times the root gives you x, so you have x cubed. I like it. I like it. I don't like this part. H over and then all that junk, right? I'm just leaving it there. Yes, that was cubed there. You didn't see that? Sometimes there's a glare on the board you can't really see. You're sitting way back there. It's okay. Yeah, there's a 3 here. Are we any happier with this situation? Why not? I don't see an h canceling, do you? Yeah, why don't we take x plus h and let's just actually cube it now. Let's do x plus h times x plus h times x plus h. Does that mean you can just do cube the x and cube the h? No, no. Life would be too easy that way, right? So I need to do x plus h cubed, which is equal to, who already knows it without doing it? X cubed plus 3x squared h plus 3x h squared plus h to the third power. Now that's what it is after you multiply it all out and get that answer. All right, like multiply it all out, collect all like terms, get everything, and boom, that's what you would get. I'll show you a way to do that quickly after I finish this example. So just, you have to trust that that's this for now, okay? Now come back up here and write it. And do you see what's going to happen? Yes. The x to the thirds are going to cancel. Man, that's a lot to have to write. Okay. Questions? Cancel out x cubed. Why is that a good scenario now? I have h's in all these terms, right? Yes. So I factor an h and cancel. I'm not going to show that step. I'll just show what it cancels to. I'm left with on top 3x squared plus, 3x squared plus 3xh plus h squared all over. That h was gone, so x plus h times square root of x plus h plus, I'm ready for spring break, x plus square root of x. Aren't you? I'm still ready for it. I know, I'm kidding. That's my way of saying, I realize that this is a grind at some point. It is grinding just a lot of stuff out here, and it's not exactly fun, but we're going to get to an answer here eventually. Should I let h go to 0 now? Oh, I forgot h is 0 there. You could only factor from the first two. But yes, but you couldn't cancel it because you wouldn't have an x plus h in this one. The only way it would cancel here is if you had another one here. It's kind of like the only reason I was able to cancel these h's is because I had an h in each term. The only way you could cancel an x plus h here is if you had it in each term. But just let h go to 0 now. So I'm taking the limit. This goes away, that goes away, that goes away, that goes away. Which leaves me with no more limit. 3x squared over x times square root of x plus x square root of x. So this is x times square root of x plus x square root of x. How many x square root of x's do I have? 2. 3x squared over 2x root x. Now can I cancel an x on the top and bottom? Yes? So I have 3x over 2 root x. Yes? Almost there. X to the first power over x to the 1/2 power. Right? That's what we have here. One of the x's here canceled. That's x to the 1 minus 1/2, which is 1/2. So x to the 1/2 is the same as square root of x. Yes? So this is 3 halves square root of x. Box it up. Oh yeah, you could do it there. You could do root x here and root x here. The bottom would become an x, and it cancels right there. You could do that also. Either way. It's not wrong. It gets you to the same result. So the question that was just posed before that one was, couldn't we have just taken this with a shortcut and done it? Yes. Check it out. Look at how easy this is. The power up here, right, is 3 halves. Bring it out front, multiply it times what was out there, which is a 1. So you have 3 halves, right? X, now subtract 1 from the power. 1/2. What's x to the 1/2? Square root of x. 3 halves square root of x. Isn't that nice? Now, what we're going to do next class is we're actually going to prove that that rule is allowed. We're going to prove it because the only way you're allowed to use the power rule, which is what it's called, is if we convince ourselves that it works for all powers of x. So we're going to do a very general answer. Use what? I know. But part of the calculus courses that we do show some stuff. That's what makes it different than the business cal. Part of what makes it different. Okay, I want to wrap up a little early today, but hold on. I want to show you the shortcut thing that I was just showing you with the x plus h. So look, give yourself lots of room to write widthwise here. If I take x plus h and I raise it to the 0 power, anything to the 0 power is what? 1. I'm putting that 1 way out there for a reason. If I write x plus h to the first power, I get what? And itself, right? X plus h. Now, look at the way I wrote that. If I write x plus h squared, that means I'd have to FOIL it, right? And FOIL and collect like terms, and you should get x squared plus 2x plus h squared. Yes? That's what you would get if you FOILed that out. Now, what if I do x plus h cubed? Now that would take some work, right? I'd have to really kind of multiply things together. But, what? Oh, yeah, thank you. I knew something looked, thank you. 2xh plus h squared. If I go one more time, it'll be x cubed plus 3x squared h plus 3xh squared plus h cubed. Again, you would just have to kind of convince yourself that that's what would happen. How about x plus h to the 4th? Imagine if you had to do that by hand. It'd be pretty nasty, wouldn't it? But you get x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. And I could keep going all day long and keep popping these things out because there's a pattern. So to the 5th power, I start with x to the 5th, right? Plus 5 x to the 4th h plus 10 x cubed h squared plus 10 x squared h cubed plus 5xh to the 4th plus h to the 5th. I'm going to explain the pattern, but I just want to make sure you see. Yeah. So let's first talk about the pattern as far as the variables. Do y'all see the pattern of the variables? What's happening to the x's as I move from left to right? They start out at the power you started with, right? So 5, and then so it's x to the 5th, then it's x to the 4th, then x cubed, then x to the 2nd, then x, and then the x is gone, right? So as you move from left to right, the powers on x go down. What about the powers on h? They go up. They start with, you don't have h, then you have h, then you have h squared, cubed, 4th, 5th. So on the next line, forget the numbers in front for now. Okay, I'm going to come back to that. What can you tell me this will be for the x's and the h's? X to the 6th plus some number, right? I'm not sure what it is. X to the 5th, h plus some number, x to the 4th, h squared plus x to the 3rd, h to the 3rd plus x squared, h to the 4th, right? Plus something x h to the 5th plus just h to the 6th. The numbers that go in here are 6, 15, 20, 15, 6. Again, I'm going to explain where they come from. You'll see it real easy here in a second. But everyone understand the powers, the property of the powers and what's happening with those. Okay. The numbers come from something called Pascal's triangle. And what I'll do is I'm going to write something in here. Everywhere that, you know, a coefficient is a number in front of a variable. I'm going to write all the coefficients here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And then, of course, 1, 6, 15, 20, 15, 6, and 1. Whew. All right. Y'all see it? Okay, now check this out. The way that Pascal's triangle works is the rule is as you draw this, do y'all see the triangle, right? As you draw the triangle, the edges always have to be 1s, okay? So you always have to 1s on the edges. And each row you go, you have to add one more term. So we started with 1 term, 2 terms, 3 terms, 4 terms, 5 terms, 6 terms, 7 terms, right? When you get to this row right here, the third one, okay, the number in the middle was the question. Where does the number in the middle come from? Because the edges are always 1s, right? The number in the middle comes from the sum of the previous 2. So look at this right here. Where does this 3 come from? The 1 and 2 above it. Where does this 3 come from? The 2 and the 1 above it. Where does this 4 come from? The 1 and the 3 above it. Where does the 6 come from? The 3 and the 6. The 3 and the 3. The 4 comes from here, right? So my 5 came from 1 and 4, 10. 4 and 6. 4 and 1. So this 1 and 5 gave me the 6. 5 and 10 gave me 15. 10 and 10 gave me 20. 10 and 5 gave me 15. And 5 and 1 gave me 6. So, what's x plus h to the 7th? Well, I know I have to start with 1x to the 7th, right? Plus, where's my number going to come from here? 1 and 6, which would give me 7x to the 6, but now here comes h. Plus, where's my next number going to come from? It's going to be the 6 and the 15, right? So 21. X is going to come down, h is going to come up. Plus 35. You see the pattern? What's the next one? 35 again. Next one. X cubed. Thank you. So now I'm at what? 21 again? X squared h to the fifth, and then we're almost there. Plus 7x h to the sixth, and then finally plus h to the seventh. I'm out of room. What if you don't have what? You don't have the chart? Well, because Pascal's triangle is pretty easy to draw by itself. So you first would have to understand the pattern in the variables. You would have to know x is going to start out at x to the seventh and go down. The h is going to start to appear. And then what you do is, okay, crap, I'm going to have to use Pascal's triangle. 1, 1, 1, 1. Edges are 1, right? Here's 2 in the middle. Edges are 1, 3, 3. Edges are 1, 4, 6, 4. Edges are 1, 5, 10, 10, 5. Edges are 1, 6, 15, 20, 15. See me? So you would have to go down until you got to where you need to go. But that's a lot better than having to multiply it out, right? I mean, you know what I'm saying? So it's a shortcut, but it's also a cool thing to just have in your back pocket. If you ever have to expand something, you know, there's... What's that? $48,000 what? Like x plus h raised to that? Then, well, we actually have a way of doing that, because these numbers, where'd they go? These numbers can actually be found a different way. They can be found using counting principles from probability and statistics courses. Have you ever heard of n choose r? Or no? N choose r? Okay. So in probability and statistics, there's a shorthand way of representing this. And so there is a nicer condensed way to write it. But as far as getting around the fact that it would be huge, you can't. But there's a short way of writing it out, I guess. That would be it. You could write out what it is in shorthand. It's using notation you haven't seen, so that's why I'm a little afraid to... Have you ever seen summation? Okay, you'd use a summation notation to whatever, 48,000, whatever it is. And then this is x to the, I'll start it out, x to the 48,000, whatever, minus n, and then h to the, start out at 0. H to the n, and then in here is your counting principle. N, 48,000, whatever, choose n. That's the way I would write that out. And a math person would understand what that is. The powers on x keep coming down, powers on h keep going up, and then this keeps spitting out that number in front. I don't know if I've addressed your question or not. So I will add one more thing. Pascal's triangle comes from a guy named Pascal, mathematician. But the Chinese had discovered it way, way, way before Pascal. So he gets credit for it because his name's on it, but just the Chinese had this written down and figured out that pattern way before he did. You can call it the Chinese triangle, I guess. I don't know. And someone probably had it before them. Homework. .2. I'm modifying the homework. So this comes off page 92. Number 3. Number 4. Four through 9. Yeah, I kind of changed as I went there. There, 3 through 9. 10 through 11 all. 19 through 23. That should be good. Everyone have a good day. Who's not here? Y'all all seem to be showing up. I'm happy with that. Are we talking today, sir? Yes. Okay, all right.